In this video, we want to evaluate the integral of 2x over x squared minus 1 using any method. And if we look at the integrand, it's a rational expression, 2x over x squared minus 1. The denominator factors into x minus 1 and x plus 1. It's in lowest terms. So we could use partial fractions. That's one method. And that's probably the longer method. This particular problem, you can work it out two ways that are fairly obvious. If we're going to do it by partial fractions, we would set it up this way. 2x over, and then factor the denominator, x minus 1, x plus 1. And because we have linear and non-repeated factors, it'll be some constant over x minus 1, another constant b over x plus 1, and so on if you had another distinct linear factor. And then it's just a matter of finding the values of a and b. One method we could use is the cover-up method. So if I cover this up here, and this right here, then I could pick any number. And you want to pick the number that makes this one 0. So here it's x equal 1. So x equal to 1 will leave me then 1 there is a 2. 1 here is a 2. And on the right side I have a. A is equal to 1. So I have the constant value for a. A is equal to 1. If I want to find b, and I cover this up right here, and I let x equal to -1. So over here then on the right side I've got b, and then on the left side -1 there is -2, -1, and a minus 1 is -2, -2 over -2 is 1. So I get b is equal to 1. That's the cover-up method. So I know the constants. Now why does that work? Because if I actually multiply through by the LCD, x minus 1, x plus 1, on the left side I'm left just with 2x. On the right side, because some of the factors cancel out, I got a times x plus 1 and b times x minus 1. So notice, if I let a equal to 1, I'm sorry, x equal to 1, then this cancels out. And this is 1 and 1 is 2, and this is 2, and 2 into 2 is 1. That's how I got this. Because this is actually an identity, so I could plug in any number I want. It doesn't have to be these same ones, but this makes it easier because it wipes out part of the expression here. Makes it easier to find the value of b. So notice here, if I let x equal to -1, this cancels out. Because you get 0 here. -1 there is a -2. -1 there is -2. That'll be -2b. Divide out by -2, we get b equal to 1. That's why the cover-up method works. Now sometimes you have a mixture of linear, and then you have some that are repeated, or you have some quadratic, irreducible quadratic factors, so that makes it more involved. So in that case, you can use a combination of the different methods. But in this case, this is what we get. This is the way this breaks down, and this is a 1, and this is a 1 here. So if I come back to this problem now, I use the partial fractions then. With partial fractions, this is going to equal 2. So this can be replaced then by the answer we got, which would be the integral of a was 1, so it'd be 1 over x minus 1, plus the b was also 1, this would be 1 over x plus 1. This is the x here. And then of course I could break this up into two integrals here, so it's really now the integral of 1 over x minus 1. If I would use a U-substitution here, this would come out over du over u, where this would be u is x minus 1. So this is just ln of absolute x minus 1. Anytime you have a linear factor like this, of this format, I think we can derive a formula for that. It's just natural log of what you have in the denominator. And this plus your constant of integration. Now, if this were a 2x here, linear, but you had a factor here, a constant here of 2, this is going to be 1/2 over here. Or if this one had a 3 here, this would be just be 1/3 right here. And of course, if you had a constant in the numerator, that would just be over this denominator, whatever you had here. Or just multiply this expression here. So that's one form of the answer. I'm going to leave it here. Now, you can also use a U-substitution, because notice, if I let u equal what's in the denominator, that's x squared minus 1. So du would be 2x. Derivative of x squared minus 1 is 2x. And there's dx. And now let's convert the integral to one involving u instead of x. So this is just going to equal to the integral of 2x dx right here. That's the du. And the denominator, x squared minus 1, that's your u. And this, of course, is your formula that leads to the natural log. Anytime you have du over u, you can have a constant here. It just multiplies that answer. It's always going to be the natural log of absolute u. So in our case, u is x squared minus 1. So just put an x squared minus 1 plus the constant integration. That's your answer. And that's the same thing as this, right? Because you can rewrite this anytime you have a sum of two logs to the same base here. You can write that as the log, in this case, natural log of this product. So the product of x minus 1 and x plus 1 is x squared minus 1 plus the constant of integration. So if you have a choice on this, obviously you'd want to use the U-substitution. You can see the steps here, from here to here. Didn't have to set up the partial fraction decomposition. Of course, this wasn't too bad of a problem because there were linear factors. But always look at the integral and see, is there more than one way to do it? Which one's the quicker or the easier way to set up the problem? This was integral was a rational expression. So usually if you have a rational expression, you look for partial fractions. I always like to look for a U-substitution. Sometimes that's the easier way or the quicker way, and that's the case in this problem. Thanks for watching. We'll see you next time.